Okay, so this is going to be a short lecture on hashing. No, just to make sure for completion, I'm going to explain this technique. Again, a brief outline. So this is also a way to support this dictionary operation: insert, search, and delete. It's all in the same scheme of things. Okay. Now, suppose the set I want to represent. Remember, our goal is to represent a set and support queries like search, insert, delete. Is a subset of some numbers, let's say 0, 1, 2, m minus 1. So that means I have an upper bound on the range of the values I'm going to store. So what I'm storing are numbers, and there is an upper bound, 25,000 or something like that. So I'm storing some small subset of numbers in the range 0 to or 1 to 25,000. For some convenience, it's useful to keep in start from 0 to m minus 1, and suppose the size is n. So n for me is much less than m. So think of it as like I'm trying to store a set of 1000 numbers in the range 1 to 10 lakh or 1 to 1 million or something like that. So m is very large and n is small. I want to store and then answer my usual questions, right? Some query comes, is that in the set? If it's not there, can I add? If it's there, can I delete? Those are my operations. So here is the solution. Okay, you can think of how you go about doing this in the special situation where I have some range and then the values I'm storing are numbers. So create an m bit vector or m bit string where let's call this string as s, and s of I equal to 1 if I is in the set and 0 otherwise. Right. So my user says here is a set 45, 27, 83, 16 is a set I want to represent, and you are told that this is in the range 0 to 10 power 6, whatever, because I do not know the values where they are coming from, but so all I am saying is what I do is create a huge string of size 10 power 6, and it is going to have 1 in the 45th, in the 27th position, you know, 16, and 83. So it's a 0 1 string vector. Everywhere else it's 0. This is my initial pre-processing step. Now think about how would I support search. The user wants to know, is 58 there? How do I know? Very simple. Go to the 58th location. If it's a 1, I know it's there. If it's a 0, it's not there. I want to insert 58. Go to the 58th location, change the 0 to 1. And if it's delete, same thing, delete 1 to 0. So all of this constant time, because the whole thing is an array. Good, we were having log n time solutions. Now we have beaten it, and we said we can do it in this special case where we know some range. I can do in one step all these insert, search, delete operations. Nothing complicated, no ABL tree, no B tree, nothing, just one bit, huge bit vector. Now, what is the drawback of this solution? You think about it for a minute, and I am sure many of you have figured out it is the space. I am representing 4 elements, but the space being used is about a million bits, which is huge. In particular, you may not know a reasonable range for your input. You have to be very conservative and store, assume it's a large number and store a lot of space. So many bits are wasted. So a way around it is what is called hashing. So what we'll do is this, that your domain is 0 to m minus 1. I want to store it in a small table. I am not going to give you that much space, because you are saying it's an n element set, n is much smaller than m. So maybe what we will do is I will create a function f, and that function is called hash function. This will take any value from 0 to m minus 1 to 0 to n minus 1, or maybe 5n minus 1, 10n, something small, not as big as m, but something small, something proportional to the size of the set you are representing, not proportional to the range. So if we come up with a function, I don't know, so let's say example, maybe h of x is x mod n. So I divide by n and take the remainder and put it there. I know that the remainder must be between 0 and n minus 1. So x, I go, if you want to represent the set element x, I will just go here and say x mod n. Okay. So I am going to store this in table. This is again nice. Now when you want to search for x, I go do a mod n, go there and see if that table has a value, then I say yes. If not, it's not there. If I want to insert it, same story. If I want to delete it, same thing. I just go do an whatever that function is, go there and see if that element is there. I just delete it. What is the problem? It's collisions. What are collisions? It's a pair of elements x, y, x not equal to y, but x and y are in S. H of x and h of y happen to be same. So both values are competing for that one particular location. Which one would you store? Well, you have to store both, because you want to store x, right? X and y, you need to store your x at S. So if you are going to decide on this, so since m is very large compared to n, there is bound to be collisions, because h is not a 1-1 function. H is mapping a huge set to a small set. There are going to be a lot of elements that are going to be collided, which may or may not happen in your set S, but it may happen. So this is called a collision, where 2 elements of your domain getting mapped to. So there are ways of resolving collisions. There are 2 ways. One is just chaining. That means you take your set S and you want to put it in the table, all elements that get mapped to this location, whatever that h of x is, all elements are put in a linked list. So that now when you come for search for an element, you map it, apply your function h, go to that location, scan through the linked list to see whether your x is there or not. Same thing with delete, same thing with insert, right? If you want to insert an element, you just go through the linked list, add it to the end. Now, you should all be asking this question in the theme of our course so far: how much time does it take for search and insert and delete? Well, in the worst case, you may be unlucky that all the elements of our set get mapped to one particular location. Okay, maybe they all have the same remainder when you divide by n, so they all get mapped to the location. Then when you do a linked list kind of a search, it's, you know, can be as bad as linear. You can maybe keep it in a sorted array, then you have a problem of insertion, which may require you to move things and so on. Okay, or you will keep it in a balanced binary search tree. Well, why are we even doing it? Then we might as well do balanced binary search trees, right? So, what I want to quickly say, this is that worst case can be order n for all these operations, for search or insert or delete, because they may all get mapped to same location. But there are, by choosing some good hash functions, one can get constant time on average. Okay, these are very loaded words. What does an average means? What is a good hash function? I am not going to dwell on these in this lecture. In fact, that's the reason I took it at the end, and I am giving you a brief session on it, just to make sure that this topic is completed and it's there in most curriculum. You may ask students to implement it, but if and it sort of works in practice for some good hash functions. But if you really care about worst case analysis, or even understand what average means, they are quite non-trivial. So, okay, so maybe I will reserve it for some advanced lectures on randomized data structures or amortized data structures. So, these are deep concept. So, just to say that hashing is very practical, works in practice, but for theoretical analysis, you should keep in mind that the worst case can be order n, and that's been our measure of success. So, it's not a great solution when it comes to worst case, but if whatever hash function you choose, it's possible that all elements get mapped to the same location by this hash function. So, there are ways to get around it, choose the hash function from a set of hash functions, maybe randomly. Okay. So, I do not want to get into the details of, because they are involved and it requires a certain level of maturity to understand it, and I might take it up for as advanced topics later on. Okay. There is another collision resolution technique that's called open addressing. So, here for example, you may or even use double hashing. So, once you have this table, two elements get mapped, maybe one element is already there, then the second element you may want to put it in the next empty spot. Remember, whatever you do during insertions, the same operation you should do during search, then only you will be able to find the element. So, you during search you come here, you find somebody, then you know that your next element may be in the next empty spot. So, you go and search there, or search sequentially in the next set of locations. Here also the worst case can be linear in the linear. So, but if hashing is there and you want to talk about it, make them implement it, you may say some different ways of doing it, but we are not going to say much more here because it does not fit into this nice complexity analysis. If I really want to do it, I have to do it on the average case time for these operations, and that requires a different level of understanding and background. So I'm going to do it. Okay. So open addressing, you know, if the table is the location is full, just maybe insert it in the next available spot. And when you are searching, you may have to again do some sort of a linear search. There is another way to do it is using double hashing. Then you know you come here, you found somebody else there, then you apply a second hash function on your element, and that may take you to a different location and put your element there and apply the same kind of an approach for search as well. I'm saying this because this is one way of dealing with the dictionary operation search, insert, delete, especially when you have a bounded range. It works in practice, and there are several ways of doing it, but worst case can be as bad as linear time. I will stop here on the discussion on dictionary problem, or in the next couple of lectures I will move on to a different set of data structure problems and we will look at solutions for them. Thank you.